Hi, this is Mike North, and today I'm going to be talking about the anatomy of a progressive web app. I have a passion for training developers in the latest and greatest modern web technologies, including JavaScript, Elixir, Ruby on Rails, and more. If you're interested in the corporate training or attending one of our workshops, check out mike.works for available courses and a schedule of events. Our story begins in 2007 with the release of the iPhone. When Steve Jobs demonstrated the web browser capabilities of this device, he brought up a page of the New York Times and showed how by double tapping on newspaper columns and on images, the browser was smart enough to dynamically resize and focus on the area of interest. For a while, this was just the nature of viewing the web through the iPhone. Web pages were designed for traditional browser sizes, and they were shrunken down when you used an iPhone into a 320 pixel wide viewport. And it took quite a while for developers to optimize sites for mobile devices. The key difference here is that instead of offering complicated dashboards that were very text heavy and offered many different options and UI elements to click on, mobile interfaces started to hone in on linear workflows and a small selection of abbreviated menu items so that it was very easy to see what you wanted and to accomplish the tasks that you set out to do. So mobile web technology started to catch on, and we saw frameworks come out like CenterTouch and jQuery Mobile. But as companies tried to do more and more ambitious things using the web as a platform, we started to see some pushback. In particular, in 2012, Facebook came out and released a bunch of press saying that it had been a huge mistake for them to use HTML5 and the web as the foundation for their mobile experience. And they basically stated that they were rolling that back and betting on native, building, independent iOS and Android apps, and maintaining those. And that was really the only way it was possible to get the user experience that they were looking for. Since 2012, the computing power of mobile devices has improved dramatically. So here you can see the two devices that were top of the line when Facebook, decided to back out of HTML5 for mobile in 2012, compared to the iPhone 6s and 6s Plus. Now, at this time, the 7 is already out, the iPhone 7, which is even more powerful than what you're seeing here. But the bottom line is we're at least an order of magnitude more powerful in general. And although this is not a JavaScript benchmark, it is a good indication that devices are capable of much more than when we were told that the web was too limiting and that we couldn't do what we needed to do on mobile devices. Now, in terms of the user experience that we're aiming for, we can offer similar things on the web and on mobile devices. So here we have side by side the experience of clicking on a restaurant review link. On the left, we have a workflow that will follow a prompt to download the native app, and on the right, we've actually already finished reaching the mobile web experience. Now you can see that in this case, the mobile web experience is quite basic. And really the idea here is to drive people to download the native app. So this native workflow is still in process, and we're going to let that continue as we move on. As we look at the benefits for the various platforms for our app. So if we build a native app, we get to enjoy a presence on the home screen, which is great. That's the subconscious advertising every time the user swipes through that page of their apps. We get background functionality like the ability to send push notifications, and we get an instant return app startup, meaning the second time they come back. Since this app is installed on their device, it can boot up instantly, regardless of the quality of the internet connection. If we build on the web platform, the advantages are that we don't need to download a huge app and install it. And you can see here in this case, this Yelp app is 82.4 megabytes compared to a web experience that is less than 1 MB. So it requires a lot less code, a lot less data, to kind of load that experience. We also get the benefit that the web is inherently cross-platform. It doesn't matter what kind of device you're using, as long as it has a web browser, you should be able to view HTML, CSS, and run JavaScript. Finally, it's very likely that you're able to share some code between your desktop and your mobile web experiences. At the very least, the part of your code that deals with, fetching data and doing non-visual things, that can be, broadly used across all of your different experiences. And I give up on waiting for this native app experience to finish up here. You can see we've finally downloaded the app, and now we're going to have to log in and then, go back to the link, and it's basically a mess at this point. One thing I want to point out is that in 2016, Google made an announcement that they were splitting their search index, meaning that starting at that point, you would get different results depending on whether you searched on a mobile device or on a desktop device. And a key, aspect of the way they're ranking mobile sites now has to do with penalizing people for these big interstitials, these big prompts that cover the whole screen, usually hiding a very bad mobile web experience, prompting you to download, this big, heavy, beautiful native app. So this hurts your SEO in a very real way. And Google has put this incentive in place, or this disincentive, I should say, because they've seen that putting this kind of user experience in front of your customers, it reduces click-through rate, right? So it turns them off, and it doesn't even help, improve app downloads. It basically is, there are no advantages to doing this. So as we look at the trade-offs between a native app and building on the web as a platform, we want to try to have our cake and eat it too. We want to find ways of getting good things that belong in both of these categories. And the way we're going to try to achieve this is through a set of technologies called progressive web apps. I like to think of progressive web app technologies as being broken into 3 categories. The first is an effort to prune the critical path. And when I talk about the critical path, I mean everything that needs to happen between your user entering a URL and them having, data-driven HTML and CSS appearing on the screen that they can interact with. We have a category of technologies that let us tolerate network instability through caching strategies and other methods. And then we have things that allow our web application to have native app-like characteristics. These include things like a home screen icon, startup splash screens, and more. So let's begin. In terms of things to look at when pruning the critical path, there are 3 metrics I want you to pay attention to. First is the time to first meaningful paint. And this has to do with when your user feels like the app has begun to finish loading, right? So they're not waiting for it anymore. And we call it a meaningful paint because doing tricks like, adding a CSS background image before the majority of your code has even landed in the browser, that is not going to cut it. If a user doesn't feel like they've finished loading, that's not what we're talking about. We want them to feel like the waiting is done, and then the next milestone is that they can interact with something. Finally, a third milestone is when we've fetched some dynamic data and we're able to render that in some fashion on the screen. In terms of what's going on in our system, let's begin with the client-side rendered single-page app. The sequence of events begins with the user requesting index.html. It returns to the browser. As it starts parsing this HTML, it may encounter script tags and links to external style sheets, and it will retrieve them ideally from a CDN. Your CSS is very likely to land first because more often than not, it's much smaller than the JavaScript, and it takes less time to parse in the browser. Later on, the JavaScript will arrive. It will be parsed from text into an abstract syntax tree, and then your app will be given a chance to boot. At this moment, we've hit our first two milestones, the time to first meaningful paint and the time to becoming interactive. We still have to go to our API and fetch some data before we can hit our third milestone here, and that'll require another round-trip network request. We can improve upon this model using a technique called server-side rendering. And the general idea is that instead of serving up an empty piece of HTML or an HTML document with an empty body and relying on the client-side JavaScript to fill it with something, we're going to serve up a pre-populated HTML document so that the client has its work done for it, at least for that first page that the user tried to enter the application through. A key advantage here is that we don't have to wait for the client-side JavaScript before we can start showing some HTML on the screen. This is better for search engine optimization and for link sharing. While it's true that modern web crawlers do execute JavaScript, and your single-page app, even if it is client-side rendered, will show up in Google and Bing's index, you do need to have server-side rendering for deeper search engine features like rich metadata, or a great example is Google accelerated mobile pages, which require basically CSS and important JavaScript to be inlined into the HTML document so that you get the complete set of functionality, style, and behavior all in one file. When it comes to sharing links on social networks and applications like Slack, you often need to add Open Graph tags and Twitter tags. These are all meta tags, and these services are far less likely to be running JavaScript in order to, allow client-side JavaScript to populate those meta tags. So you want to make sure that your HTML document has that data already present and ready to go. One thing you have to watch out for when dealing with server-side rendering is that there are subtle but important differences between Node.js JavaScript and browser JavaScript. An obvious example is that the window global variable is only available in the browser, and that browsers can do AJAX requests while Node.js cannot. When server-side rendering, we want to make sure that we're, whenever possible, trying to avoid doing the same work twice. The approach that the React and Ember.js communities take is to take the application state after server-side rendering has completed, serialize it into the HTML itself, so that when the client-side app boots up, it can read this data and basically seed the store with that initial state, which avoids the necessity to make those same network requests again as client-side re-rendering takes place. One key thing that I want you to be aware of as we look at how this changes our system diagram is that oftentimes you're going to put your asset serving layer, which is responsible for rendering your HTML, and your application API in the same data center, or in a, so that they have a very, very fast internal network connection between them. This is important because fetching data from your API in order to build this server-side rendered HTML happens much, much faster than communication between your user's browser and the API. So if we look at what a server-side rendered single-page app looks like, the user will request index.html. The asset serving layer will then go and get data from the API. This may be repeated one or more times. It will come back, the HTML will be assembled, and it will be returned to the browser. At this point, the browser starts parsing through this HTML document. It encounters external style sheets and scripts, goes and fetches those from the CDN, and as soon as the CSS lands, the app is already painted on the screen and it is already interactive. In fact, we get our third milestone at this point too, because the server took care of populating this HTML with data in advance. So we've taken client-side JavaScript off of the critical path to becoming, to achieving our first meaningful paint, to becoming interactive, and to rendering data on the screen. Later on, this JavaScript will arrive, it will be parsed, the app will boot, and unbeknownst to the user, at this point, client-side rendering and client-side navigation is taking over, and we will be operating as a traditional single-page app. So the next optimization we're going to look at has to do with caching. And caching is something that is so often done poorly or in an incomplete way. Most valid and robust caching strategies that I've seen fall into two categories. The first is something I'm going to call immutable content. Using the immutable content strategy means that once you publish a URL, such as a JavaScript file, you never overwrite that file. A common approach to this is to hash the file's contents itself, getting the MD5 checksum or a similar value, and taking that value and putting it in the file name so that if at any time the contents of the file change, so will the file name, and you will get a unique URL. When you can rely on URLs' contents never changing, that allows us to give our browser instructions to hold on to this cache data for a long time. Eventually, the data will be evicted from the cache after it remains unused for a period of time. But we can safely allow the browser to do its thing and not worry about any interference between different versions of our app. In this strategy, index.html is what unites all of the static assets that correspond to a particular version of our app together. It will refer to a style sheet and an external JavaScript, or one or more style sheets, one or more external JavaScript files that are all meant to work together. This approach is offline friendly because we can cache a particular version of our app, and even if we manage to cache everything that we need, we should be good to go. The check with the server strategy allows URLs to be rewritten, meaning you're publishing potentially like a vendor.js file over and over and over, rewriting the contents of vendor.js multiple times each time we deploy. In this situation, we want to use the cache control option called no cache, which doesn't mean that we're instructing the browser to abstain from caching, but rather we're saying that it should make a head request in order to determine whether the server or the CDN says that this resource has been modified since the browser last saw it. Usually it will make this judgment on the last modified or the e-tag headers for this resource. This comes at a cost in that although we don't necessarily have to download these files every time, we do have to make extra network requests, and that takes time even though it's not a lot of data that's being sent back and forth. What we can layer on top of these caching strategies is something called a service worker. Service workers are JavaScript workers, meaning they're a separate process that runs in addition to the usual JavaScript single thread, and they serve as programmable network proxies. Because service workers can potentially monitor and modify requests, they only work over HTTPS. This is designed to prevent potentially catastrophic man-in-the-middle attacks that would be accomplished by modifying the service worker's JavaScript and allowing a malicious proxy to be injected between your application and your API. Service workers have a predictable lifecycle that works in the following way. When the browser detects a service worker and it is registered, the service worker goes into an installing state. Once the installation process has completed, the service worker is then considered to be activated. If any problems occur during the installation process, the service worker enters and stays in an error state. Once activated, the service worker becomes idle and then can respond to any fetch requests. In the event that There are no pending fetch requests that the service worker is currently handling, and no pages are currently consuming the service worker. It becomes terminated and then returns to an idle state upon revisiting that page and triggering a navigation event. Service workers provide us with a vast array of caching strategies that can layer on top of and work with HTTP caching. The first strategy we'll look at is called pre-caching, and it begins with a cache being provided with a list of important resources, which it then downloads in advance during the installation process of the service worker. Later on, when an app says that they need one of these resources, the cache already has it and is able to provide it and resolve that request instantly. In the network or cache strategy, the app requests a resource, and then the cache goes and retrieves it on behalf of the application. This seems like it's operating as usual, as the proxy is just letting the request pass through and continue off to the CDN to retrieve the image. But what we can add on top of this is a time limit, where if the request takes too long, we essentially abandon it and resolve with a cache resource that we already have in memory. Additionally, if something goes wrong, for example, if the image that was asked for is not found, we can reply with a standard, image missing resource, rather than letting the browser, have its default no image response. This would let us have potentially a placeholder image that could be used across our whole app whenever we find that there's a 404 upon requesting for an image. The cache and update strategy involves the app first asking for a resource, the cache providing any data it already has stored in memory, and then immediately going out and fetching a brand new copy of the resource. Potentially, this could be a new version of it. This works really nicely with using the last modified header or the e-tag header, as it plays nice with HTTP caching. A twist on this, called the cache update and refresh strategy, involves the service worker going out and then upon retrieving potentially a new file, sending a notification to the app through post message, and essentially telling it to load this new resource. This allows us to have all of the benefits of serving up resources instantly, while also being able to replace them or leave it up to the app's discretion to replace them immediately after updated data is retrieved. Service workers are available in most evergreen browsers. I know you're probably looking at that yellow indication on Safari. Apple is historically very secretive about the features that they release in their browser, so it's likely that we won't hear anything until it lands in a Safari technical preview, at which point it will be a complete implementation of some sort. In terms of what introduction of a service worker does to our, where we last left this diagram, which was a server-rendered single-page app, essentially we can put it in between our CDN and our user, giving it the ability to apply any of the caching strategies we spoke about earlier in the event that we see, that we have data in memory. This will allow our app to retrieve these heavy, large files instantly and, dramatically improve the boot process for our app. And you can see that the three important times that we're looking at, the first meaningful paint, the time to interactive, and the time to data visualization, those all are basically a tiny amount of time beyond the cost of downloading index.html itself. In terms of storing addressable content, that is, things that are available at a particular URL, service workers are excellent. But sometimes we have different types of data, things that aren't necessarily addressable. A great example for this would be a record that a user might create while offline. It doesn't have an ID, it doesn't have a URL yet, so we need to store it somewhere. So two of the options that have been around for ages are cookies and local storage, but these are problematic for several reasons. First, they just store string values, and so anything that can't easily be serialized to a string is going to be problematic here. They're not worker-friendly, meaning they can only be accessed on the main JavaScript execution thread, not from a JavaScript worker. So the service worker can't directly touch these things. An often overlooked option that is available on a wide range of browsers is IndexedDB. This is a versioned, indexable, worker-friendly, durable storage system. It supports many types of values, ranging from strings and integers and functions to even blob data, so you could store potentially like an image that you're getting ready to upload at a later date. So it's not a SQL database, it doesn't support structured query language, and it's not a relational database. It wouldn't be totally wrong to think of this as almost like a light MongoDB in the browser. And it works in the following way. We begin by opening a database. And on this open object that's returned, we can attach handlers for two events. The upgrade needed event serves as a place for us to set up our initial schema and migrate the schema as our database structure evolves. The way I like to handle this is with a case switch statement, allowing old versions of the database to be incrementally upgraded bit by bit to the current version. For example, if the current version of our database in our service worker code is version 19, and a user we haven't seen in a while shows up and they have version 3, they will begin executing database migrations at case 3, and that will upgrade them from 3 to 4, and then they'll go to case 4, and that'll upgrade them from 4 to 5, and so on. They'll sort of insert into the migration stack and then fall through all the way to the end, bringing them up to current. All of the rest of the work is handled by creating and executing transactions in the onSuccess hook. IndexedDB is supported in a very wide range of browsers, ranging from IE11 to the most recent several versions of all of the evergreen browsers. An additional optimization that we're going to apply is something that Google calls the app shell architecture. When applying this pattern, we will model your app as an instantly loading, largely static shell consisting of usually a high-level navigation and the topmost level UI elements, and then dynamic content that is populated therein. This allows us to load the shell instantly by caching it, and then wait for a server to give us some dynamic data. So if we look at how applying IndexedDB and the app shell architecture, how that will affect the diagram that we last looked at, here is our starting point. This is where we last left off. And as we go to the second version of our progressive web app here, we need to be aware of two different scenarios. The first being the user visiting us for the first time. In this case, we will go pass through the service worker because it won't have any cache data for us, go to our CDN, retrieve the assets, and then come back. So this basically matches potentially a server-side rendering case here. Additionally, once our app is done booting up and once the user starts using it, we will ask our rendering server for the shell HTML, and we will start, we'll create or migrate our IndexedDB and start populating it with records. Later on, when our user returns, the flow will look as follows. We'll ask our service worker for the shell HTML, and then we'll send out in that shell HTML, we'll have references to external style sheets, external scripts. Those will return to the browser nearly instantly. And at that point, we've reached our time to first meaningful paint and our time to interactive. The JavaScript will then be parsed and your app will boot, after which we can go and retrieve some records from IndexedDB. And we'll start visualizing data on the screen. This is a big deal because essentially we haven't introduced a dependency on a remote resource yet. And this means that we'll be able to boot and show some data on the screen even when we're offline. Of course, typically you'll be online and you can begin requesting data from the API and updating any cached records that you're storing in IndexedDB accordingly. So we've looked at two of our three important elements of the progressive web app set of technologies, the last of which is called app-like characteristics. And this is where our web application starts to look and feel like a native app. These characteristics range from home screen icons to splash screens that pop up while the app is booting up, and they're usually accomplished by way of meta tags. Here's an example of a meta tag that will get rid of the browser UI, meaning the address bar, in the event that it's launched from what Android would call a web clip or what iOS would call a home screen bookmark. App icons can be added with various link tags and can be defined on a per size basis, depending on which device needs each size of icon. We can provide an explicit bookmark name that will be used instead of the title tag. And this is useful if the title tag ends up being very long and we need a short bookmark tag because the number of characters allowed are much more limited. And then finally, splash screens can also be applied by link tags. And again, this can be defined on a per size and per orientation basis. A relatively new advancement in terms of this kind of metadata is the web app manifest file. And this overlaps to some degree with things that can be defined in meta tags and link tags, but with some important new additions. You can see here, one of my favorites is the start URL. This has to do with the fact that bookmarking an app by adding it to your home screen means that forever, when you launch that app, that is the URL that you're going to enter through. So if you're viewing a particular article on a newspaper site, and then at that moment decide to add to home screen, forever, when you launch that, that web application, you're going to start at the URL for that article. Start URL lets us define a more conventional starting point when users reboot the app. So this is very important in terms of making it feel like an app instead of a bookmark. Recent additions to these app-like characteristics that are available for the web include the ability to process secure payments. So on the left here, we've got Apple Pay, which can be used in mobile Safari. And in Chrome for Android, we can use Android Pay, which is similar in that the device itself holds references to the billing information, and it exposes a token to the consuming app, which is a very safe way to pay because the recipient of the payment never really gets the credit card number, so you get to hold that private. In the future, we can expect new developments in terms of these app-like characteristics, which include push notifications by way of a service worker, background sync by way of service workers, and first-class framework support where we don't have to build on top of the low-level IndexedDB and service worker APIs, but rather can have sort of a plug-and-play approach to applying different caching strategies. IndexedDB has some efforts that around something called IndexedDB 2.0, which are enhancements around the indexing features of this database. And finally, HTTP2, when used in combination with any of the things that we've been talking about, promises to add further performance improvements through eliminating the need to do the SSL handshake repeatedly on a per request basis. So as you can see, when we compare this progressive web app system to the conventional client-side rendered single-page app, things are getting really, really complicated. There are a lot more moving parts. The only advice I can give you, given that we're all going to be building these kinds of apps in the next couple of years, is that you should take whatever steps you can to reduce the number of decisions that you must make, so there is room in your thinking and in your bandwidth to handle managing all of these other pieces of your system, which are brand new. It's very clear that the momentum moving towards progressive web apps is unstoppable. It's inevitable that we're going to all have to worry about managing these different things. So my pitch is, get trained. I'm offering a progressive web app fundamentals course with simple labs, and we'll be offering this a few times in 2017 in Europe. Visit mike.works for details, and keep an eye out for future announcements about other courses in modern web technology.